Welcome everyone to the WERA 103 presentation today. We're very happy to have Dr. Clain Jones addressing some issues about soil acidification in the Western United States, an issue that is getting increasingly important as this acidity problem continues to develop. So we'll hear from Dr. Clain Jones and his experience with this. Let me briefly introduce Dr. Jones. Dr. Jones received his bachelor's degree from Cornell and then moved to University of Washington for his master's degree and then received his PhD in soil chemistry in 1998. Since that time, he's been working at the Montana State University as an extension soil fertility specialist. Clain has a lot of experience dealing with soil problems on how to increase crop productivity and how to manage this important natural resource to get its maximum value for us. So it's a real treat to hear from Clain today. And with that introduction, I'll go ahead and turn the screen over to Dr. Jones and let him talk about his subject today. So welcome.
Thank you very much, Rob. The topic that I'm covering today, soil acidification, is a topic that I didn't think I was going to have to cover in Montana during my career. It's something that's popped up since 2015 in Montana, and I know it's been more prevalent in some other Western states like Idaho and Washington and Oregon previous to that time, a couple decades previous to that time. So this first picture shows one of the problems with identifying acidic areas within a field, and that is that they tend to start fairly small. So looking at this first screenshot, you can see there's an area with very poor growth and a pH of 3.8. This is the lowest we've measured in Montana to date. Just a few yards from that same location is an area that's pH 5.1. Notice the crop here looks perfectly good. However, we know somewhere below pH 5, we start seeing crop problems, and somewhere below about 4.5, we start seeing crop failure. If you do have any questions after you watch this presentation, please feel free to give me a call at the phone number shown. That should be area code 406-994-6076, or send me an email. A lot of the work I'm showing today was work that was conducted by my colleague Rick Engel here at MSU. So today I'm going to show the prevalence of acidification in Montana, and I know there's similar issues in surrounding states. I'll review acidification's causes and contributing factors, show what low pH soil affected crops look like, and then discuss steps to prevent or minimize acidification. This is a map of Montana showing our 56 counties. Any county that has a circle in it is a county where there's at least one field that has pH below 5.5 as reported by a crop advisor, an extension agent, or a producer. The ones that have stars are counties where an MSU employee has verified that that pH is below 5.5. One thing that stands out on this graph is the regionality of the low pH. There's quite a few counties in western Montana that have pHs below 5.5. Not a big surprise in that this area receives somewhat more moisture for the most part than eastern Montana, and that's leached some of the basic cations and calcium carbonate out of the surface soil. The big prevalence of low pH counties in this region, these are largely dryland cropping areas where nitrogen fertilizer has likely helped cause this low pH. And then we have another area in Montana, in northeast Montana, where dryland annual cropping is more prevalent. The areas where we haven't seen this issue is primarily in southeastern Montana and far southwestern Montana. These are more of our range and livestock areas where there's not as much annual cropping and therefore lower nitrogen fertilizer rates. So there's a number of natural reasons for low soil pH. They tend to occur in areas where we have soils with low buffering capacity, meaning low amounts of soil organic matter, coarser textures, some granite rather than calcareous soils. Also, historical forest vegetation soils generally have lower pH than historical grassland. In Montana, we don't have many ag soils that were historically forested, but in northern Idaho, for example, there's quite a few in that category. Also, regions with high precipitation that can lead to leaching of both base cations and also nitrate. And I'll explain why leaching of nitrate can exacerbate this problem. In addition, areas that have high precipitation generally have higher yields and therefore receive more nitrogen fertilizer. There's also a number of agronomic reasons for low soil pH. For example, ammonium-based nitrogen fertilizer that's applied above plant needs can cause low pH due to a process called nitrification. Nitrification is where ammonium or a urea-based nitrogen fertilizer in the presence of air and water gets converted over to nitrate plus acid. If a substantial portion of this nitrate leaches, that makes the problem worse. The reason for that is that if there's less nitrate uptake, then roots will release fewer what's called basic anions. So anions such as hydroxide or bicarbonate. A plant can't accumulate positive charge, nor can it accumulate negative charge. So if a plant takes up a bunch of nitrate, it needs to release a bunch of hydroxide and bicarbonate. If instead that nitrate leaches out of the root zone, it doesn't do this and it doesn't help buffer this produced acid. Turns out mathematically and chemically, if a plant uses every last molecule of nitrate, there should be no net acidification, but that is rarely the case. Also, crop residue removal can lower pH because it removes what we call our basic cations, our base cations such as calcium, magnesium, and potassium. In addition, no-till can concentrate the acidity where the nitrogen fertilizer is applied. So no-till doesn't cause this problem, but it can make it worse in certain areas. Traditionally, when soils were tilled somewhere between 4 inches and maybe 14 inches deep, those low pH areas were mixed with higher pH areas at depth. And so we generally do not see this problem in heavily tilled fields, at least yet. No-till, however, we end up having low pH very near the surface, which is where most nitrogen fertilizer is applied. Legumes, when legumes are planted, such as pea, lentil, or alfalfa, they can acidify the rooting zone through nitrogen fixation. And research indicates that perennial legumes do this more so than annual legumes. However, this effect of lowering pH essentially naturally through N fixation seems to be much less than fertilizing of wheat and other cereals. This graphic shows how concentrated these low pH areas are near the surface of our soils. So here we have soil at 5 different locations across north central Montana, showing depth, increasing depth in the soil from 0 to 25 inches. Notice that near the surface, in the top 3 inches, pHs of these 5 locations all are about pH 4 to 4.6, an area where crop growth is definitely impacted. Moving down just a few inches in the soil, the pH jumps up to 5, a place where sometimes we do not see growth issues. And notice when we jump up to 9 inches, the pH is close to 7, an area that's not close to being acidic. By the time we get down below 20 inches, the pH is close to 8, and most of these soils have a fair amount of limestone. Excuse me, a fair amount of limestone in them, which ends up buffering the pH near 8. This is some research done west of Bozeman, Montana, in a 16-inch rainfall area that shows fall soil pH in the top 4 inches after 14 years of nitrogen fertilization on a dry land system. Here we focus on 3 different cropping systems in this 14-year study, where we had a 10-year CRP, Conservation Reserve Program, planting, which was primarily alfalfa dominated with some perennial grass in there, followed by 4 years of a pea wheat rotation. This, of course, didn't need very much nitrogen, and we had a pH that was very similar to when this study started, somewhere around pH 7.3. In a continuous wheat system that had a low rate of nitrogen, meaning half the rate of nitrogen that I or MSU would recommend, this required a fair amount more nitrogen, somewhere around 1,200 pounds of nitrogen per acre over 14 years. And that dropped the pH to about 6.7. When that continuous wheat was instead applied with a high rate of nitrogen, meaning somewhere around 3 pounds of available nitrogen per bushel of yield, which is essentially what is recommended in MSU, notice the pH dropped to 6.2. Now, this isn't an area where we expect to see yield or growth problems, but what's scary to me is this large drop occurred in just 14 years. So another 14 years, we might expect another unit pH drop, and then we will start running into acidity issues. This works out to be about 0.06 pH units for each 100 pounds of nitrogen per acre applied. So you can picture this pH drop can be fairly quick, especially under high N rates. What about in an area that's somewhat drier, up in Big Sandy, Montana, and north central Montana? This is a shorter term study, a 6-year study, where we are showing the results from 2 different nitrogen rates: no nitrogen applied and 3 pounds of available nitrogen per bushel applied. And then we tracked soil pH in that 6th year. And we did that under 4 different cropping systems. So fallow, a legume grown for grain, either lentil or pea, spring wheat, and then green manure, all followed by winter wheat, abbreviated WW. Notice that in all 4 of these cropping systems, at the higher N rate, again, the recommended N rate, pH has dropped about 0.3 units over these 6 years. A little surprising to me, though, is that cropping system didn't seem to matter very dramatically. And in fact, cropping system was not found to have a significant effect on pH, where nitrogen rate did have a significant effect. At this site, 100 pounds of nitrogen per acre decreased pH by 0.15 units. So this is a little scarier still, meaning the same amount of nitrogen dropped the pH by substantially more than in that previous study. And you might be asking, well, why the faster rate? Well, I think it primarily has to do with that term called buffering capacity. This is a fairly coarse soil, a sandy clay loam. That's about 50% sand. The previous study was conducted on a silt loam with higher organic matter than at this site, which was a very low organic matter site, somewhere around 1.1% organic matter. So the same amount of nitrogen dropped the pH faster because the soil was less buffered. So how does soil pH affect nutrient availability and the toxin availability? This is a graphic that shows as soil pH drops from 7.5 down to 4.5, the availability of calcium, magnesium, and nitrogen, sulfur, and potassium both drop. Phosphorus availability as pH drops, it actually goes up, and then somewhere around pH 6 to 6.5, it starts falling off, and by the time we get to 4.5, its availability is less. Molybdenum has kind of a similar curve. So some plants go hungry for some nutrients. Nutrients can be lost to the environment at low soil pH, and aluminum, magnesium, manganese, and other metals, their availability goes up to the point that we can actually see toxicity. The most toxic of these metals seems to be aluminum, followed by manganese. This is some results, again, from my colleague, Rick Engel, showing this toxic aluminum and the amount of extractable aluminum. So the amount of extractable aluminum seems to be fairly directly related to the amount of toxicity we see in plants. Notice at pHs above 5.5, the amount of extractable aluminum is essentially 0. When we get somewhere around 5, we start getting measurable levels of aluminum, and by pH 4, we have very high levels of aluminum. To put those numbers in perspective, toxic level of aluminum, extractable aluminum, is somewhere around 5 parts per million. So we don't need to get much below about pH 5 to start seeing toxicity. The other thing that's shown on this graph is how important the depth of soil is. So at 0 to 3 inches, this is where we generally see these really low pH levels. From 3 to 6 inches, we see moderate. 6 to 12 inches, again, we see these low levels of aluminum. And this is primarily because where Montana farmers have been putting their nitrogen fertilizer and where nitrification has been occurring is in the top 3 inches. In Saskatchewan, at least in some locations, it's believed that manganese is the larger problem resulting in toxicity. This graphic shows some results from a 10-year study where they applied different nitrogen rates from 160 pounds of nitrogen per acre down to no nitrogen. And then in the 10th year of this study, they tracked manganese levels from the time they applied fertilizer, a little before they applied fertilizer, till 25 days after they applied fertilizer. What they found was that just a few days after applying fertilizer, about 5 days, is when these manganese levels spiked. Also notice that the more nitrogen that was applied historically, the higher these manganese levels are, and somewhere around 10 or 12 parts per million is where wheat becomes very sensitive to manganese. And so you can see if they applied less than about 40 pounds of nitrogen per acre, they didn't run into any toxicity. 80, they flirted with that toxic level, and 160 pounds of N per acre, they had more manganese, likely because they had more nitrification and lower levels of pH. So one of the first things to do is you first need to find out whether you're a crop advisor, an extension agent, a producer, is do you have this problem? And what I would first look for is unexplained poor health in low or mid-slope areas. Also, dig up your plants. One of the best indicators of aluminum toxicity is what's called club roots or witch's broom roots, where the roots kind of fan out from one place, or as shown in this pea plant, they're very stubby. In fact, they look very similar to nematode damage. Above ground symptoms of aluminum toxicity, including smaller leaves, short or thick internodes. So the internodes are the space between the stems. This graphic here shows a healthy wheat plant, and then this shows unhealthy. So notice that the leaves have some yellowing. There can be a lot of yellowing along the margins. There can be these pinched off areas, sometimes purple or brown lesions and indentations, and then again some leaf withering and collapse in the center of the leaf. There's some similarities to nitrogen deficiency, but nitrogen deficiency is usually more uniform than aluminum toxicity. How about manganese toxicity? Manganese toxicity shows up as cupping or crinkling of leaves. It can also show up as chlorotic and reddening spots, moving over to necrosis, which simply means cell death or tissue death. It often starts on the older leaves, meaning the lower leaves, especially at the tips and the margins of those leaves. Acid soils may have many additional negative impacts, not just to aluminum or manganese toxicity. One problem that's been observed is persistence of weak acid herbicides. So some herbicides will degrade more slowly under low pH conditions. So I know in Washington State and also some, we think in Montana, we see more problems in these lower pH fields, and sometimes we think herbicide persistence and herbicide damage might show up before aluminum toxicity does. And so I know in the Pacific Northwest, for some of these herbicides, there's actually longer rotation intervals if the pH is lower. Rhizobia do not like low pH, so the rhizobia, which form nodules on legumes, appear to be more sensitive than crops are to low pH. Somewhere around pH 6, nitrogen fixation starts falling off, where again, crops by themselves, non-legume crops, see problems below about pH 5. Cephalosporium stripe will do better in low pH conditions along with some other fungal diseases. And then some have postulated that just the hydrogen concentration, which is the element that's causing these acid soils, might be toxic directly. And it's not just aluminum or manganese causing the problems. So scout and soil test, look for unexplained poor plant health, so something you can explain by, say, poor drainage or maybe a over application of herbicide and under application of fertilizer. I would look at your pH on prior soil tests from composited field samples. If you have fields that have pH less than 6, I would bet that you have probably some areas that have pHs below 5. We often have been finding pHs as low as 4.5 on the same fields where we see pHs around 7. And so the problem with compositing samples across the field, which has been done for decades to get kind of an average field nutrient level, can mask problems. And so, for example, if 8 of your 10 soil samples have pHs above 6, and then 2 have pHs below 5, when you mix those all in a bag, you might get a pH somewhere, say around 6.5 or 7, and not know you have a problem. And that's why my second point here is if you have pHs above 6 and below 7.5, don't assume you have no areas with low pH. Make sure to scout and maybe do some sort of grid sampling. If you have pHs consistently above 7.5, you likely don't have a problem. You can field test in the field with either pH color strip kits. You can find those online. You can find those at aquarium stores. You can also buy fairly inexpensive what's called pH sticks, which are similar to pH probes, except they're all in one unit rather than a probe and a meter. It's basically a meter on a stick. I would recommend doing those pH tests in the top 3 inches. If you do, say, the top 6 inches or the top 9 inches, you can end up masking a problem because of that issue I showed earlier where you can have much higher pH down at, say, 6 or 9 inches than in the top 3 inches. I would then confirm what you find, meaning confirm by sending soils to a laboratory. Even though I like the strips and the sticks, it would be best before, say, you spend a lot of money on lime to actually verify that you have pHs either below 5 or potassium chloride extractable aluminum, which is what many labs will run, greater than about 5 parts per million. I would also recommend maybe doing that next depth, the 3 to 6 inches, if you or the producer is considering tilling. There's no sense in trying to till to solve this problem if your 3 to 6 inch depth has as low a pH as your 0 to 3, but we sometimes find very high pHs in that 3 to 6, and you might be able to buy yourself some time by doing some vertical tillage. One thing to keep in mind is that pH varies seasonally and annually. So if you're looking for trends over time, I would recommend testing from both the same area, the same time of year, and the same lab to make sure that any changes you're seeing are real changes rather than maybe some sort of seasonal change or maybe a difference in lab technique. So what can you do to prevent acidification? Basically anything you can do to increase the efficiency of nitrogen fertilizer use. That includes things like soil testing as close as possible to application time. Make sure you have enough other nutrients. So if you don't have enough phosphorus, potassium, or sulfur and your crop is limited in its growth by one of those nutrients, it's going to waste the nitrogen that's applied. I'd suggest using a conservative pre-plant rate, and then if it does rain as much or more than you were thinking, you can top dress later. Also applying nitrogen as close to as possible to peak crop uptake time. Also plant lower nitrogenating crops, including pulses like pea, lentil, and chickpea. Planting perennial forages, and on my website, we have a list of acid tolerant varieties. Also reducing nitrogen rates, especially when protein discounts are low, and using variable or site-specific rates. So you could apply less nitrogen in low production areas limited by variables other than nitrogen. So for example, in low pH areas, it would be a waste of money to apply more nitrogen since the crop is limited by pH and not nitrogen. Plus you end up getting more leaching, which makes the problem worse. What about possibly changing the nitrogen source? So I would suggest minimizing use of ammonium fertilizers, meaning monoammonium phosphate and ammonium sulfate. Each unit of nitrogen in those will produce twice the acidity of each unit of nitrogen in urea or urea ammonium nitrate. You might also consider using calcium ammonium nitrate, where there's some evidence that it lowers pH less than urea or liquid solutions such as 28 solution or 32 solution. Most calcium ammonium nitrates have limestone embedded in the product, and so there's a little bit of buffering from that limestone. You could also consider including legumes as your nitrogen source or manure as your nitrogen source if either is available. This is a graph from work done out of Mandan, North Dakota by Mark Liebig, where he compared the pH changes from growing a perennial forage for 5 years versus growing spring wheat for 5 years. He tracked soil pH in the top 2 inches over time from 2007 to 2011. Note that when spring wheat was grown continuously, that pH gradually dropped. It did show some variability, but there was a gradual drop with time, whereas the perennial forage showed a gradual increase in pH with time. And note by the end of the study, a relatively short study, 5-6 years total, the pH difference between the perennial forage and the spring wheat was about 0.6 or 0.7 pH units. That's huge. That's the difference between having potentially in another 10-15 years having an acid soil and not having an acid soil. Also think about your crop selection. So different crops have different tolerances to soil pH. This graph shows the maximum attainable yield ranging from 30% up to 100% as pH increases from 4.8 up to about 5.7 for 6 different crops. So how to read this graph is it shows that all the crops get 100% yield as long as the pH is fairly high. But when the pH drops below about 5.2, a high tolerant, meaning an aluminum tolerant wheat crop actually starts showing some yield reduction. Barley starts showing yield reduction below about 5.3. Low tolerant wheat somewhere below 5.4, and then the 3 legumes shown here, peas, lentils, and alfalfa, are all fairly intolerant to low pH somewhere below about 5.5. So you might be seeing a contradiction. I recommended planting legumes instead of cereals to save on nitrogen fertilizer. However, they don't do very well in low pH. And that's why I think scouting is so important. You don't want to wait till you have pH 5 to try to prevent this problem. You need to prevent this problem up at pH 6 when you can still grow other crops and have a little more flexibility in your crop management and your nitrogen management. This is a figure that shows how variable different cultivars are to low pH and aluminum tolerance. So for example, some of these crops do very well down to pH 5.5 or so. This crop does well down to about pH 5.3. These two cultivars here do very poorly. Looks like there's hardly going to be any crop at low pH. So there's work being done in Oklahoma, Washington State, Idaho, Montana, likely Oregon, looking at aluminum tolerant crops. And I would keep in touch with your local breeders and see what aluminum tolerant crops or varieties that they can recommend. If the pH does come down too low and you simply can't get it higher by changing your cropping system, you're probably going to have to lime. Some things you're going to want to know about your lime source are the calcium carbonate equivalent, the lime score, the current soil pH and the desired pH, also likely the buffer pH, and then have a target. Somewhat you're going to want to lime to above 5 to reduce aluminum toxicity, probably closer to 5.5 to have some buffer, and then greater than 6, you'll probably be good for at least 10 years. Also probably going to want to know your desired crops, since different crops have different tolerances. You can get a rate from a soil testing lab. They will measure both your pH and your buffer pH. Or you can calculate using an equation developed by Washington State University, where they found a fairly good relationship between the final desired pH and liming rate. And currently, researchers in Washington, Montana, Oregon, and Idaho are conducting research towards specific recommendations for their states. This issue of low pH and liming has been around in the Midwest and Southeast parts of the US for decades. They've already established this type of information. This issue is newer to us here in the Northwest and the Western US, and so we're still developing recommendations. And then a cost-saving measure would be to only lime field areas with low soil pH. Again, we're finding that in general, less than a third to a quarter of most of these fields with low pH actually have a low pH issue, and it's going to be a waste of money and time to lime those higher pH areas. One relatively inexpensive option is to use spent sugar beet lime. So sugar beet factories will accumulate this lime. Often they don't have a use for it. So here in Montana, we have a couple plants where lime simply accumulates and the factories are looking to get rid of it. Some problems is it's heavy, so shipping costs can be high. It can have some moisture if it hasn't been tarped, and it can clump. You might need a wet lime spreader to spread it. Sometimes it even has trash or some chunks. And we found that you need to incorporate it with tillage for best results. If it just sits on the surface, it doesn't get down into those top few inches very quickly and mitigate the issue. We might need rates as high as 3 to 6 tons per acre to bring the pH to above 6. So those are fairly high rates and can be expensive just to haul this material. So to summarize, cropland soils are becoming more acidic, largely due to nitrogen fertilization. This reduces yield for several reasons, as I mentioned. Sound management of nutrients, crop, and residue can help slow or prevent soil acidification. Crop and variety selection can help adapt to acid soils. And liming, perhaps tilling or planting perennials can help mitigate or actually even reverse acidification. If you want more information on anything that I've discussed, as well as additional information I didn't have time to discuss, you can go to my soil acidification website shown at this link. And if you have questions about how pH is measured or what a buffer pH test means and how to use it, you can go to my colleague Amber Moore's YouTube video, also done in the same WIRA series, which is an excellent summary of how to interpret these various tests. And I finish with this photo of a limed and unlimed field from a photo taken in Oregon in 1926, partly to point out that in some areas of the West, this is not a this is not a new issue, and it's been going on for at least 90 years.
Well, thank you, Dr. Jones. This has really been an interesting presentation to point out how soil acidity is really becoming an emerging issue for crop production in the West. So we will be learning more about this in the years to come from your research, and look forward to interacting with you on this in the future. So thank you for your presentation today, and we'll invite everyone else to participate in the other WERA 103 presentations on our YouTube channel. Okay, thank you.
Thank you, Rob.